We are going to break down a data structures interview question that tests your ability to manipulate array indices with strict precision. Our task is to take an array containing an equal number of positive and negative integers and rearrange them so the signs alternate. The final sequence must always begin with a positive number. There is a secondary constraint we have to follow. The original relative order of the elements must stay identical. If a 3 appears before a 5 in the starting array, the 3 must appear before the 5 in our final array. The same rule applies to the negative numbers. The challenge lies in maintaining that specific index gap for the alternating signs while preserving the relative sequence of every element in the input. We will start by establishing the most intuitive step-by-step separation method as our baseline solution. In our first pass, we iterate through the original array and pull the elements apart. We place all the positive integers into one list and all the negative integers into a second list. Now we execute a second pass to weave them back together into a final answer array. We draw from our separated lists, placing the positive numbers exclusively at the even indices, 0, 2, and 4, and placing the negative numbers at the odd indices. Because we loop through the data to separate the numbers and loop again to merge them, this requires O of n time. We also build 2 new sublists, meaning it requires O of n extra space. Attempting to swap elements in place to save space often fails here. Because we must preserve the original relative order, moving one number to an earlier index requires shifting every other element in the array, which quickly turns a simple loop into an O of n squared operation. This 2-pass method proves you understand the rules, but we can achieve the exact same result without allocating 2 entirely separate lists. We can optimize this process into a single array traversal by utilizing 2 independent pointers. Looking at this diagram, we set up an empty answer array and initialize our pointers. To guarantee the alternating pattern from step, we check the sign of each element. When we encounter our first positive number, we place it directly into the answer array at our current positive index. When ahead 2 spaces at a time, we ensure that every positive number lands on an even index, leaving the odd-numbered slots empty and ready for our negative elements. The negative numbers use the exact same placement logic, but they execute on the odd indices using the negative index pointer. We find a negative, place it, and increment by 2. By the time we finish our single pass through the original array, we have woven the elements into their correct alternating positions. This approach eliminates the overhead of managing multiple sublists. While the space complexity remains O of n to host the return array, we have condensed the logic into a single traversal. Now, let's adapt this logic for a common interview variation. What happens if the array has an unequal number of positive and negative integers? If we try to apply our 2-pointer logic to an unbalanced array, it breaks down. The pointers will leave empty gaps and eventually try to jump past the end of the array bounds. The required rule for this variation is to alternate the signs for as long as mathematically possible, and then simply append the remaining excess elements to the end of the array. To achieve this safely, we need to return to our separation method, pulling the elements into a positive list and a negative list. Next, we find whichever list is shorter. We iterate exactly up to the length of that smaller list to build the cleanly alternating section of our final array. Finally, we take the remaining elements from the larger list and drop them straight into the back of our answer array. This fills out the rest of the array without altering their original relative order. Solving this variation requires recognizing when a specific optimization no longer fits the constraints. Reverting to the separation method handles the logic of a variable length tail much more reliably than forcing a 2-pointer solution designed for balanced inputs. We started with a basic separation strategy to understand the ordering constraints, and then refined it into an optimized single-pass pointer technique. Both approaches run in O of n time and O of n space. However, the optimal method builds the final array directly on the first pass, requiring no secondary sublists to keep track of the elements. Recognizing how array indices map to parity, evens and odds, provides a clear path through the problem. It sidesteps the complications of shifting elements in place, keeping the logic tied to simple index increments. Conquering this problem solidifies your foundational array logic. If this breakdown helped you see the math a little clearer, please like and subscribe, and continue your interview prep with our full data structures and algorithms playlist. Keep practicing.